Good morning, everybody. I'm Dr. P.S. Kaushik, Principal at Sri Digambar Institute of Technology, Dausa, Rajasthan. This is lecture number 26 on the subject Engineering Mechanics. In this lecture, we will be dealing with the basics of moment of inertia. Let us recollect what we learned till now in this subject. In the very first lecture, I introduced you with the syllabus of the civil engineering branch. There are few additional topics for mechanical branch that I will take after completion of civil syllabus. We studied about the force, system of force, basic laws of mechanics, then conditions of static and dynamic equilibrium, then moment, then principle of moment, couple. We studied about the friction, then truss system, then the centroid and center of gravity. These must topics we have till now covered in this subject. The next 4 lectures we will be studying about the moment of inertia. A quick note on the CG and centroids. The centroid or center of gravity of any object is the point within that object from which the force of gravity appears to act. An object will remain at rest if it is balanced on any point along a vertical line passing through its center of gravity. It means whatever is the orientation of the body, the position of center of gravity will remain unchanged. The centroid of a two-dimensional surface, that is line or area, is the point that corresponds to the center of gravity of a very thin homogeneous plate of the same area or shape. If the area or section of the body has one line of symmetry, the centroid will lie wherever along the line of symmetry. For example, if this is the T section, it is symmetrical about this vertical axis line. So you can say that the centroid will lie somewhere over this line. Where it will lie, that will depend upon the dimensions of these two rectangles, that is rectangle 1 and rectangle 2. This was the point of consideration here. If the what is moment of inertia? Then it is a measure of an object's resistance to change to its rotation, also defined as the capacity of a cross section to resist bending. It must be specified with respect to a chosen axis of rotation. It is usually quantified as meter ki power 4 or kg meter square. That we will be explaining in the next 3-4 slides. Moment of inertia. As we studied that the turning effect of a force is called moment. Mathematically, it is equal to the product of force and the shortest distance, that is vertical, from the moment center on the line of action of the force. The moment of force mathematically is written as F into x. X is the shortest distance on the line of action. For example, if this is the moment center, this is the a member over which a force is acting like this here. Then what we have to do is just set it back. This is the moment center O, and the force is acting like this here, making an angle of theta with the horizontal. Then this is the force P. If you extend backward the line of action of the force and draw a vertical over it, then if this is x, then it will be defined as P into x, that is moment m. Okay. If we multiply this moment of force again by x, that is shortest distance, then it is called moment of moment or second moment or moment of inertia, that is F into x is equal to F into x square, called moment of moment. Or second moment. Now if we replace this force by mass or area of cross section, then we will be calling it that mass moment of inertia or area moment of inertia. Now what is the significance of this? That we will be discussing in the very next. Just once more, we know the turning effect of a force is called moment. We studied in the unit 1. Then if we multiply the moment again with its moment arm magnitude, then we will be calling it second moment or moment of moment. And if we replace this force by area or by mass of a section, of mass of a body or area of a section, then it will be called as mass moment of inertia or section moment of inertia. This is your mass moment of inertia, this is your section moment, usually denoted by capital I. Significance of moment of inertia. Let us recollect the Newton's first law first. We know that in case of rectilinear motion, mass is the cause of inertia and the force is the agent to counter that inertia. As we know, a body tends to remain in rest or uniform motion until unless an external force is applied, that we are studying from class 8th standard. Here, now, here we did not mention which type of force or motion that is. If it is a rectilinear motion, then we call it the rectilinear inertia or simply inertia we call. Inertia is the tendency of a body or a mass to remain at rest or in uniform motion. An external force has to be required to give a change in state from rest to motion, or if body is in motion, then the acceleration or deceleration is required. For that you require an external agent in the form of force. Okay. Now, more is the mass of the body, more will be the force required to change the state of rest or uniform motion of that object or body. Here we have shown two figures. Simply, one is this is here he is pushing a rock here, and when rock is of more weight, then he is trying to push it from back with the extreme pressure. Here I wanted to signify the importance that more is the mass, more is the force required to change the state of rest of uniform motion. This was my intention here to show this figure. Now, from the Newton's first law of motion, as we know that body tends to remain in rest or uniform motion until an external agent in the form of force is applied on it. Now, inertia, as we know, is the tendency to remain in the state of rest or uniform motion, and the resistance to change in the state of rest or uniform motion is called the moment of inertia. Here, again, inertia is the tendency to remain in the state of rest or uniform motion. A resistance to change in the state of rest or uniform turning moment. Here, important is turning moment. Turning, which in earlier I could miss it. This is the effect turning. Important factor is this was. So, the resistance to change the state of rest or uniform turning moment is called moment of inertia. It is the moment of inertia, that is, and thus it is the inertia against the turning effect or torque. What I told you earlier, the turning effect of a force is called moment. A moment is of two types, that is turning moment and bending moment. Bending moment we denote it by M, a turning moment we denote it by T. Again, let us recollect that if this is a member, it is a cantilever, say, beam, and this is its centroidal axis. If you apply a force here, it will give a bending effect to this. This moment, this will bend like this. But, and then the moment will be called bending moment M. Now, if you apply a couple, that is a force here and a force here, and try to rotate it like this, the algebraic sum of these forces will be 0. That forces are opposite to each other. One force is acting like this, other is acting. That is, so it will have a pure twisting moment, and that twisting moment is called torque, or here. Mass moment of inertia. In case of rotary motion, moment of inertia is turning inertia of mass, and the countering agent is the torque, T. Turning effect of the force we call. More is the moment of inertia, more will be the torque required to change the state of rest or uniform turning motion. Here, I am giving you two practical examples which you may have come across. This is a mudman, that is Kumkar, making mud pots on a wheel. Usually, when there was scarcity of electricity in the olden days, it would have been a stone wheel having an anvil in the center, and that man used to rotate by a wooden rod, turning it like this for very fast, and then he used to keep mud in the center and give it shape of a pot, and in doing so this wheel used to rotate for 10 to 15 minutes continuously, and in that time he used to make 10 to 15 pots. Nowadays it has been replaced by a electric motor driven wheel, but earlier it used to be a heavy stone wheel with an anvil at the center axle, on which this wheel used to rotate. Okay, this is the case of, because more is the mass, and that is mass is and more is the its inertia, that is turning inertia. Similarly, case is this is the flywheel of an engine. This is an old steam engine on a on a rail. That is, it used to have a huge flywheel. The tendency of this wheel is to maintain the rotation when there is no force, driving force is there. For example, in the next lecture we will dealing in the IC engine, the flywheels, and many more, 5 to 6 more examples of real life we will be dealing. So I am leaving it here only for the next lecture. Here, area or section or structural moment of inertia, very important for you civil engineers. This is the beam under construction. These are the iron rods being connected together by the rings. Where you can see that it is having a cross section like this. This is the cross section. Its depth is more than its cross sectional dimension, because, just for your information till as of now, that if for a rectangular section, this this is the centroid axis xx, this is yy. If this is the d and this is the b, then ixx is bd cube by 3 and iyy is d b cube by 3. Means the cube is of the dimension which is vertical to the axis. If ixx, this is the vertical, and you will come to know when we will doing the strength of material part of this subject, some part, that is unit 4, then you will find that the bending moment, there is a equation m upon I equal to sigma bending upon y equal to E upon R. So I is the moment of inertia. So in this section here, this section will be strong against bending against about this axis, x axis. So we have to make this I more, we have to increase this dimension. Vertical dimension is to be increased because it will be having a cubic effect. So it will be having more moment of inertia for bending. As you know, this is the stress generated in the beam. This is the moment, bending force, bending moment, and this is the moment of inertia. So it will resist more bending moment for the same stress if its vertical dimension is more. That's why this beam is made rectangular. You can see in the building where in the college building also, that depth of the beam is more compared to its width. Further, this is again an example of a newly constructed building. Here you can see that this is the column and this is the beam. You can find the depth of the beam is very large compared to its width. This is made only because we want to increase the bending strength of the beam, because it will be having a lot of weight of the slab we are going to make over it. In case of structure, area moment of inertia is the inertia of area section, and bending moment m is the countering agent. More is the area moment of inertia about an axis, more will be the bending moment required to deflect or bend the structure about that axis. The area moment of inertia is the geometrical property of a beam, and it depends on a reference axis about which it is to be measured. So, for area moment of inertia to be moment of inertia, what we require? We require a cross section area, and the cross section area of best geometry. A best geometry for resistance against bending is the I section. I section is the best section for resistance against bending, but for construction work, it is difficult to manufacture a I section, so they usually make a rectangular section of this shape. Factors affecting the moment of inertia. First, mass moment of inertia of a body is independent of its angular velocity. It depends upon the position of or orientation of the axis of rotation, shape and size of the body, and the distribution of mass of the body about the axis of rotation. Then for area moment of inertia, it depends upon cross-sectional area of the member, the geometry of the section that I told you earlier, and the distance of outer fiber vertical to the reference axis. Now, this much was an introduction to the moment of inertia, and for your information, it is really a tremendous property, and you will find many uses of this. And in the next lecture, I will be dealing with the practical application of the moment of inertia in the real world. Thanks for watching this video.